Alright, so in the previous class we realized that we need to find out, given linearly independent set, how do I make it into an orthonormal set or orthogonal set, or how do I make them perpendicular to each other. Alright, so let me give you a definition of orthonormal set, orthogonal set. I just stated them. So let V be an inner product space, fine, a collection of sets, a collection or a subset S which is equal to U1, U2, UK of V is called an orthogonal set if inner product of Ui and Uj is 0 for all I not equal to j. Alright. So I am talking of orthogonal set. Orthogonal means they should be perpendicular to each other. They should be orthogonal to each other. Then there is a word what is called orthonormal. Orthonormal set. So when I talk of orthonormal set, then it is orthogonal. So I need Ui, Uj to be 0 for all I not equal to j, and the length of each vector should also be 1 for all I. So here it is orthogonal and unit vectors. So I have got all the unit vectors and they are perpendicular to each other, they are orthogonal to each other. Is that okay? So there are two things that are important. One is just looking at orthogonality, that they are perpendicular to each other, and there is that you are looking at only unit vectors, fine. So you have to be careful about them. So example, so if I look at these vectors 1 0 0, 0 1 0, 0 0 1, this is orthonormal. Even if I look at this vector 1 1 1, 1 minus 1 0, so this is a subset of R3, this is orthogonal, fine. Even this vectors 1 1 1, 1 minus 1 0, 1 1 minus 2, subset of R3, this is also orthogonal, fine. Now if I want to look this from the point of view of orthonormality, I have divided by the unit vectors, so make it unit vector. So 1 1 1 divided by root 3, 1 minus 1 0 divided by root 2, 1 1 minus 2 divided by root 6. This will give me an orthonormal set. Alright. So I have given you enough examples of orthogonality and orthonormality here, fine. Even though this looks cumbersome to you because of root 3, root 2, root 6, this is much more desired as compared to orthogonality, alright, as far as we are concerned. Because everything is in terms of unit vectors, so calculations and ideas are more fruitful as far as orthonormality is concerned, fine. So let me just prove the first statement. So we have proved that, we have given the statement that a collection of vectors U1 to UK, they are called orthogonal if something happens. Is that okay? That's more important, that orthogonality means there is perpendicularity between them. Now the question is that given an orthogonal set, is that set linearly independent? So question 1, let S is equal to U1 U2 UK be an orthogonal set in an inner product space, fine, some inner product space, then S is linearly independent. So let's try to prove this part, proof or the solution of this, fine. Now if I want to prove something is linearly independent or dependent, I need to look at the system of equation. So consider the system, consider the linear system, alpha 1 u1 plus alpha 2 u2 plus alpha k uk is equal to 0. In the unknowns, alpha 1, alpha 2, alpha k. Fine. Need to show S is linearly independent, which is same thing as saying that the only solution of a star is the trivial solution. All right, I do not have any other solution except the trivial solution. All right, so let us try to compute it. So let us look at inner product of the zero vector. So this is zero vector with any, say with u1. Suppose I want to look at inner product of these two. All right, fine. Or let me write the other way around, I think. Otherwise, so I want to look at u1 and the zero vector. I want to look at this part. So this is my zero vector. Fine. So I know that inner product of any vector with 0 is 0. So I know that this is 0, but this is also equal to, no, I think I written it correctly. I had written it earlier itself, that was correct. So 0 comma u1, so this is my zero vector. Fine. So this is same as, I am looking at this system which is same as alpha 1 u1 plus alpha 2 u2 plus alpha k uk. So 0 is this vector, and I am looking at this with inner product with u1. So by definition of inner product, this is same as alpha 1 u1 plus alpha 2 u2 plus alpha k uk u1 here, which is same as alpha times u1 plus alpha 2 times u2 plus alpha k times uk u1. This is same as alpha times u1 square plus alpha 2 times, my set was orthogonal. Now since our set was orthogonal, it means that inner product of u2 with u1 is 0 and so on till alpha k times 0. Oh, this is alpha 1 here as usual, the same as alpha 1 times length of u1 square. Fine. So this implies alpha 1 is 0 as norm of u1 is not the zero vector. All right. Fine. So you have to be important, you have to understand this here. When I am saying that something is orthogonal set, I didn't say in the beginning, I think I forgot to state here that zero vector is not allowed here. So zero vector is not allowed in the orthogonal set. Vector does not belong. Or whenever you want to say that a vector is orthogonal to somebody else, 0 you don't want to include because 0 is orthogonal to every vector. All right. So therefore you do not consider zero vector as such. Is that okay? So now we have shown that, oh, that was the question, but where is the definition? Definition of orthogonal I gave before, is it? No, I gave it here itself. Fine. So what we have shown here is that if I have an orthogonal set, then that set is linearly independent. Fine, that is one thing. Second thing, which is again very important, is that let B is equal to u1, u2, un be an ordered basis of any vector space basis V an inner product space with dimension of V is equal to n. All right. Since the dimension of V is n, this is indeed a basis, therefore I wrote it as ordered basis. So there is this. Then what we know is, then if I want to compute, then if I want to write any V, then for any V belonging to V, if I want to compute coordinates of V, alpha 1, alpha 2, alpha n, if I want to compute, find alpha i's such that V is equal to alpha 1 u1 plus alpha 2 u2 plus alpha n un. If I want to find this alpha i's so that I can write coordinates of V with respect to basis V as alpha 1 to alpha n, then I need to solve a linear system. All right. And so I'll have to put the value of what the vector u1 is, what the vector u2 is, what the vector un is, and form a system of equation, solve it. It takes time, but I can do it. All right. Because u1 to un is linearly independent, so there will be a unique solution, and therefore I can write it. But to get these alpha i's, it takes time. I have to do a lot of extra work. Fine. But suppose I assume extra condition. So extra condition as extra condition u1 u2 un, this set is also orthonormal or orthogonal itself. Suppose I want to say it is orthogonal. All right. So if I say it is orthogonal, then things are much simpler. Why? Because let's look at, if I want to say it is orthogonal, then I want to compute what is alpha 1, for example. All right. So what I will do, I have been given this V, I know that V looks like this, and looks like this means I have to find alpha i's. Fine. So let us look at inner product of V with u1. Inner product of V with u1 will be alpha 1 u1 plus alpha 2 u2 plus alpha n un comma u1. So if you go look at the previous one, it is same as alpha 1 times norm of u1 square plus alpha 2 times inner product of u2 with u1 plus so on plus alpha n times un and u1, which is same as alpha 1 times norm of u1 square. All right. So what it tells me is that this will imply that alpha 1 is nothing but inner product of V with u1 divided by length of u1 square. That's all. So in place of solving a linear system and getting the coordinates, I can get them directly as such. This is more important for me, that I don't have to do any calculation. I just have to find out the inner product to get my coefficients here. Is that okay? That's one thing. Something more. So let this u1 u2 un be an ordered orthonormal basis. So ordered orthonormal basis means ordering is there and each of these vectors are ui's length of ui is 1 and inner product of ui with uj is 0, I not equal to j. All right. So all these things are given to me. Ordering is given to me. Orthonormality means length 1 and perpendicular. All right. This is given to me. Then if I want to compute, then if I want to write v with respect to b, then this is nothing but just look at v with u1, inner product of v with u1, inner product of v with u2, v with un. So just compute the inner product and you get the coordinates directly. So coordinates of v with respect to b. All right. So there is nothing, you don't have to solve any system, you don't have to do any work, the length is already 1, so you don't have to divide anything, you just have to look at the inner product to get your answers. In the previous one what we had was, we had to divide here, divide by norm of u1 square, we have to divide it because we didn't say the length was 1. Now here we are assuming that the length is 1, so it is just those inner products. Is that okay? Now what we are trying to say here is, understand it, very important. What we are saying is that I am not wasting my time trying to find out things. So in some sense we are trying to look at this here. So let me just write it. So if I am writing the vector say 2, 3, 1, 4 as, so 2, 3, 1, 4 is nothing but, it is 2, 3, 1, 4. So this is with respect to the standard basis. Let me write it, a standard basis. What is the standard basis? E1, E2, E3 and E4, they are standard basis. So if I look at the standard basis as my say B, A here, then this with respect to A is basically B. Why it is this? Because this is nothing but, so if I write this vector as V, then V comma E1 will give me 2, V comma E2 will give me 3, V comma E3 gives me V1, V comma E4 gives me 4, alright, or this is what I am writing here, fine. So in some sense what we are saying is that whatever we could do for a standard basis, in a standard basis everything was nice, I just had to look at the first component, second component, third component, fourth component, and they came as inner product with respect to the standard vectors E1, E2, E3 and E4, fine. What we are saying here is that forget about E1, E2, E3, E4. If you have any ordered orthonormal basis, then a similar thing can be done, fine. Is that okay? That's one thing, you can just do it. Second thing was, if I want to find the length of the vector, if I want to find the length of V, so this was my V. If I want to find the length of V square, length of V square was nothing but 2a square plus 3a square plus 1a square plus 4a square, which is same as V comma E1 square plus V comma E2 square plus V comma E3 square and V comma E4 square. This is also possible here. So even with respect to this, so with respect to this B, I still have that it is summation. So this is same as writing as V comma UI, I going from 1 to n, fine. Here it was, V was, so I wrote it as somewhere, no I didn't write it, 2 times E1 plus 3 times E2 plus E3 plus 4 times E4, alright. Similarly we are writing it here, I write V as this, and this implies that length of V square is same as, look at V comma UI, square it, I going from 1 to n, I get this part. Is that okay? Let us look at the proof of this. Proof is very simple, so I will just do it, which is very easy, so I will do it. So if I want to look at norm of V square, it is nothing but inner product of V with V itself, which is same as I going from 1 to n, V comma UI, comma j is equal to 1 to n, V comma uj, which is same as I going from 1 to n, V comma UI, fine. The small one, this big one will come for this UI, comma j is equal to 1 to n, V comma uj, alright. Now there is a small thing that you have to be careful. So let me write with a red here, that if I am looking at complex numbers, not real numbers, then this will not make sense. I will have to put a bar here if I am looking at complex, fine. If I am looking at real, there was no problem. Now see here, this is what is going to happen. So this will be equal to, or let me write it here itself, first line, I is equal to 1 to n, you have V comma UI. Now if I want to take this out, this is the second coordinate, so I will have to write in terms of j is equal to 1 to n, V comma uj bar, I will have to do that because it is the second component, and then it is UI uj. Is that okay? UI with uj, fine. This into ui uj. This is what I have. Now what we know is that these ui's are orthonormal, so they are perpendicular, so they are 0 here. So if I am looking at I is fixed here, alright, j is a variable here, j is going from 1 to n. So I will get some contribution from here only when j is same as I, otherwise it will be 0. So therefore I can write it as summation I going from 1 to n, fine, v comma ui. As I said, this is 0 equal to 0 unless j is equal to I. So I will be left out only with here v comma ui bar, fine, and I will be left out with ui, but this is also 1 because the length is 1. I have taken it as an orthonormal vector. So I am left out with I is equal to 1 to n v comma ui and v comma ui bar complex conjugate, and therefore this is same as I equal to 1 to n v comma ui this square, alright, because z bar is nothing but mod of z square, alright, for any complex number z. So therefore when I am looking at real numbers, I don't need to put this absolute value square, but when I want to look at complex, I have to put this extra line and the square of this, alright, because of this part. So you can see that whatever we could do for Pythagoras theorem was this. I have a similar result here for the general setup also, fine. That's very important for us, so you have to keep track of that, fine. Now the next idea using this, which is again important, is this part. So let me write that part. So let V be an inner product space with u1 u2 un as an orthonormal set, fine. Not saying that S is a basis. We are just saying it is an orthonormal set, we are not saying it is a basis, fine. Then what we are going to do is, let us look at this part. So then for any v belonging to V, this vector V is equal to, so for any V, define W is equal to summation I is equal to 1 to n V comma ui, then this belongs to linear span of S, and V minus W is orthogonal to every element of S, right. So this is very important, this concept. So what is the concept? Understand it nicely. I have something which is an orthonormal set. From there I am getting a W, fine, and then I am looking at V minus W. We are saying that V minus W is perpendicular to every element of S, and therefore it will be perpendicular to all the linear combination, and hence it is also perpendicular to W, fine. So it is similar to, recall what we had, that I had a projection, so there was this vector, so I had U, we wrote U as U minus U comma V divided by length of V into V. This was orthogonal to V, plus we had U comma V upon length of V into V. This was the projection of U on V, alright. So understand it nicely. We decomposed earlier U in terms of something which is perpendicular to V and which was parallel to V. We are doing the same thing here. We are decomposing V into V minus W plus W. What is W? W is projection. So W is projection on linear span of S, alright, and this is orthogonal to linear span of S. Fine. So be careful, understand it very nicely. The proof is very simple, but I want you to understand this. Fine. So let's think about it, what we are doing, just the generalization of what we had. So recall, I wanted projections to be on each of them. So recall that example which was, I think, 1 1 0 0, 1 0 1 0 and 0 1 1 2. So there these vectors were not orthogonal. So we could not talk of projection onto each one of them and then add it, all right. But here we are starting with u1 to un which are perpendicular. So it is perpendicular, so I am able to add those projections. So there I am able to projection. So look at this, since ui's are orthogonal here, so if I want to write it in terms of this part here, it will be u comma ui and ui itself, all right. This is what it is. So each of these components here, each of them is projection onto ui, fine. So each of the elements v comma ui is the projection of v on ui. Is that okay? So I am adding all the projections and then getting the vector w. Is that okay? So I am just writing a component of this part as this, which I wrote it as w here, and which is orthogonal to it. Fine. All right. So I'll just end the lecture here itself. Thank you.